Hi, I'm Sangbin Moon. I'm going to talk about my project on communication-efficient Newton-type methods for distributed optimization. Before getting to the recent algorithm, let me first explain some background. The problem of our interest is distributed learning, and the motivation behind this is twofold. Modern machine learning applications, in many cases, deal with a large amount of data, which we call big data, that are sometimes cannot be stored in a single machine. Therefore, instead of trying to gather data in one place, we want to leverage the storage as well as the computing power of multiple machines. And Newton's method is an iterative process to find the solution of an equation, such as g of x equals 0. If we apply this update formula over and over again, x will converge to the solution of g of x equals 0. Now let's extend this idea to a distributed optimization problem. SGD, or stochastic gradient descent that we are familiar of, has this update formula of subtracting the gradient of a function to find the local minimum. Instead of this formula, Newton's method uses the inverse of Hessian, which is the gradient of the gradient. If you recall from the previous slide, this formula finds the solution of the equation gradient of f equals 0. Newton's method is known to find the optimal W faster than SGD. But the problem is that Hessian is a matrix, while gradient is vector. Therefore, if we want to collect this information from multiple devices, the communication overhead becomes big O of d squared instead of d. And the algorithm of our interest, called GIANT, tries to solve this issue by sending a vector instead of a matrix. But how do we do that? If we send H, it is a matrix. But if we send H inverse times G, it is a matrix vector product, which is a vector. In standard Newton's method, individual local Hessians are aggregated to find the true global Hessian, which is the arithmetic mean. But in GIANT, we are technically aggregating the inverse of Hessian. And the approximation H tilde is essentially a harmonic mean. Therefore, the essence of GIANT is to approximate an arithmetic mean, which is the true global Hessian, with a harmonic mean. Finally, let's look at the evaluation result. In the final paper, I compared GIANT with other two recent algorithms, but here I only have time to explain one algorithm, so I compared GIANT with a standard Newton's method. First, looking at the lost progress on the left-hand side, two methods are almost identical. Standard Newton finds the solution in 6 iterations, while GIANT finds in 14 iterations. GIANT is a little slower because it uses an approximation, but they are comparable, as you can see. On the other hand, if we look at the communication cost on the right side, GIANT requires far less communication burden on the network. So we can see the benefit of the approximation. So this is what I have for today. Thank you for listening.